So my talk is about investigation of zinc aluminate as a refractory material. It's my PhD dissertation defense, and thank you all for being here. Um, I will go straight into the topic. So this presentation has like different parts. First, I will start with introducing the concept of refractories and chrome refractories, and then why we need like chrome-free refractories. Then I'll go into the four main projects of my PhD thesis. The first one is optimization of the dilatometer to synthesize aggregates. The second is magnesium titanate, refractory aggregate manufacturing, then zinc aluminate, and then bonding of this zinc aluminate phase with commercial aggregates so that it can be used in like real world applications. And then finally an overall conclusion and then future work. So introduction. So refractories are high temperature ceramics, and these are used to make every major material. So I'm studying materials engineering here, and materials engineering has, like four like metals, polymers, and ceramics. And what you see here is that there's RHD gasser, which is used to make automobile grade steel. It has a vacuum chamber. It reduces the hydrogen and oxygen, all the gases, as well as it reduces the carbon content by oxygen blowing. So this is RHD gasser, where we use macrome refractories. This is a glass tank furnace used for making glass, which is used in a construction as a window glass. So this is all alumina, zirconia, silica. The top is silica crown. You can see molten glass here. This is a cement rotary kiln which used to be lined with magnesia chrome. Now it is lined with magnesia spinel. The operation temperature is 1450, and then you have this fluid catalytic cracking unit which runs at around 540 degrees C, which is used in petrochemical refining. So what you see here is that refractories are essential to contain heat and to process all other kinds of materials. So you need refractories to make materials. And the consumption of refractories is directly related to the construction business, which is again directly related to economical growth of a country. So consumption, if a country consumes more refractories, so it indirectly says that it is in a growing phase. Now, what you see here is that refractories are very heterogeneous. So you see here, there are like large particles called aggregates, which can go up to 3 millimeter in size. Then there are small powders, which forms the matrix, which bonds the aggregates together. And then you have intermediate sized particles. And roughly the aggregates are 30 to 40 weight%, the matrix is 30 to 40 weight%, and the rest is intermediates. This is an example of a direct bonded magnesia chrome. By direct bonding, I mean there are these large magnesia particles, periclase particles. These are chromite grains, and these are fused or sintered macrome, like pre-synthesized or pre-formed macrome. And these are bonded together by this complex chromite spinel solid solution. So hot bending strength or a 3-point bending strength at a high temperature at 1450 degrees C, 1500 degrees C, the main deformation mechanism is due to sliding of these grains assisted by this liquid phase in the intergranular regions. So, but in direct bonded macrome, the silica content has been intentionally reduced to below 1%. So there is this spinel, chrome-based spinel bonding phase, which creates a direct bond between aggregates and matrix, and as well as aggregates of magnesia with chrome aggregates, and that gives it very high hot strength. But there is problem is that at high temperature, this macrome or this chrome present in these refractories and also in alumina chrome, it can react with slag. It can react with alkaline vapors and form hexavalent chrome compounds. There are different compounds like calcium chromate, then chrome hawine, and the US limit, the permissible limit for this hexavalent chrome is 5 milligram per liter. And there are reports where they have actually quantified the hexavalent chrome content in used refractories, and they have found 30 to 50 times the permissible limit. So this is a real problem. This hexavalent chrome is a real problem. It causes cancer. It contaminates the groundwater. So there needs to be a replacement. And actually, it has been replaced in cement kilns, which runs at 1450 degrees C, but at 1600 degrees C and higher, there has been no replacement. So when I started this PhD thesis, I was tasked with finding the next best chrome-free material. And I went into this periodic table, which is the abundance of elements in the Earth's upper continental crust. And what you see here, what I saw here is that all below this blue rare earth line, everything is expensive, and refractories are primarily made with abundantly available ores, like things like alumina, silica, magnesia, things like that. So what I found here is that any of this lithium, boron, then potassium, sodium, these all form low melting oxides, low melting phases with traditional refractory materials. So you cannot use this to make the next chrome-free material. Then what I found is that this iron, manganese, calcium, silica, these are actually components of the slag themselves. So to resist a slag, I cannot use the same oxides. And this tin is again below the rare earth, so it's rare earth. There has been some work on magnesium titanate spinel, but then it forms low melting phases, and also it's like expensive. And then strontium, barium, they also form low melting phases, low melting oxides. There was one good thing, which is graphite. Even though magnesia carbon is used in steel ladles, but in RH degasser, where magnesia chrome is primarily used, oxygen blowing oxidizes this graphite phase and it causes degradation. So I was left with magnesia, alumina, titania, and zinc as the main chrome-free materials. And again, zirconium is a well-known material, refractory material. And I found that if I want to make something which can compete with magnesia chrome, where again this mag chrome is used in basic slags because almost 60% of the refractory is made of magnesia. So we need, in order to withstand a basic environment, we need enough basic substance. So by basic I mean MgO based material. So MgO is a main phase, and then you have spinel, and we need a bonding phase. Just like Macrome has a chromite spinel bonding phase, we need something to bond and improve the aggregate matrix bonding, and that will improve the hot MOR, that will improve the erosion resistance. So zirconia has already been tested, and I published this 2 years back as part of my master's work. And what we found here is that the hot MOR doubled due to zirconia addition. So now we need something new. We need, what can be even better than that? And that's when we found this magnesium titanate and zinc aluminate. Both of them has a spinel structure. This is an inverse spinel. This is a normal spinel. And then this magnesium aluminate is a normal spinel. By normal spinel, I mean the magnesium ion resides in the tetrahedral sides. The aluminum ion resides in the octahedral sides. Whereas in magnesium titanate, which is an inverse spinel, half of the magnesium resides in tetrahedral and half in octahedral, and the titanium resides in the octahedral sides. So you can see that there's like all of these are cubic spinels, but there is some differences, but then they all, due to the similarity in crystal structure, they all go into solid solution. Because of the four, like the four rules for solid solution, in which the same crystal structure and like similar ionic size, that plays a big role. I think it's called Hume-Rothery rules. So anyways, so you have magnesium aluminate, magnesium titanate, you have complete solid solution at like firing temperatures, usual firing temperatures. Not only that, when you cool it, you have this precipitation of the two end spinel members along with magnesium. This is called Gay-Kielite phase. So all of this can help in bonding. In macrome bricks, the same phenomena happens. There is a chromite solid solution, and when the brick cools down, there is precipitation of the part of that chromite phase, and that enhances the bonding. Zinc aluminate, again, it has full solid solution, isomorphous solid solution. So it will, all of these zinc aluminate and magnesium titanate can enhance the bonding as compared to magnesia spinel. So this side is magnesia, this side is spinel. You can see there's barely any solid solution. So magnesium titanate, zinc aluminate can bond with magnesium aluminate, and that's why they are the main part of my PhD thesis as chrome-free alternative materials. So not only there is that bonding, which you can see that in situ magnesium titanate increases the porosity. The red line, the red right side is porosity. You see the porosity is increasing, and strength decreases exponentially with porosity. But what you see here is that hot MR is not changing much. It's almost constant. So this means that magnesium titanate has a very good solid solution with magnesium aluminate, which is resistant to high temperature deformation. If we could somehow stop this porosity from generation by using preformed magnesium titanate aggregates, which I have done, then we can stop this porosity and increase the hot MR. Not only that, this magnesium titanate can react with slag. This is RH slag, which is my past work. And what I took some samples out from this slag refractory interaction zone, and I did XRD, and I formed calcium titanate. And this calcium titanate has a very high melting point. It forms like a barrier at the interface, and this calcium titanate slag barrier prevents the penetrating slag from penetrating downwards deeper into the refractory. So this enhances the corrosion resistance. So magnesium titanate has good corrosion resistance, as well as it has the potential to increase hot MOR. Zinc aluminate, it has already been published in the last 2 years by different groups that it can improve the hot MOR by 3 times of alumina castables. Not only that, and this is due to the high solid solution zone between alumina and zinc aluminate, or also called garnite. So there is this high solid solution zone. Not only that, you see that these are hot elastic modulus measurements, and this is alumina zinc aluminate castable. You see that at 800 degrees C, the strength is increasing, and this is very important because in this temperature zone, the castable is very weak. All its cement has dehydrated. There is no bonding phase, and that's when, if this intermediate temperature strength increases, then it's a really good thing. So zinc aluminate makes castable stronger. The same when zinc aluminate has been combined with magnesium aluminate spinon as well as alumina, we see the same thing in the blue curve. The above 800 degrees C, the strength increases. So zinc aluminate can increases hot MOR, and it can increase the corrosion resistance. So this is a comparison between zinc oxide and zirconium oxide with iron oxide, which is a main slag component. Iron is very famous for being very corrosive component of slag, corrosive oxide of slag. So what you see here is that whenever you have zinc oxide, the melting temperature is higher, 1610 versus 1525. Again, there is no eutectic here, whereas there is a eutectic at 1330. So what you see here is that previously I told that zirconium oxide, when you add to spinet, it increases hot MOR and corrosion resistance. Now you see that zinc aluminate has even better potential. So all of these slides tell you that magnesium titanate and zinc aluminate, these two phases have a very high potential in increasing hot strength, which is related to erosion resistance as well as slag corrosion resistance. Now coming to the porosity aspect. So this literature tells that the pore formation in magnesium aluminate and magnesium titanate during the in situ reaction, by in situ I mean magnesia is reacting with alumina to form magnesium aluminate during firing of the break or castable, whatever that is, there is this volume percent expansion of 7.6% due to the density difference. This is all the at molecular weight divided by the density. You get the volume change per unit mole. So what you see here is that this volume change increases the porosity, and porosity in a refractory weakens it. This is a magnesium titanate from my previous work. You can see there is this large amount of porosity due to in situ magnesium titanate formation. This is all, these P-marked grains are MgO, and there was titania in the matrix. This titania formed magnesium titanate, and it pushed the grains apart, and you have a lot of porosity, and that decreased the strength of the material. Now, coming to zinc aluminate, there is not much volume change in this in situ zinc aluminate formation, but there is this extreme Kirkendall effect. So what happens? Normally, say in magnesium aluminate, there is a two-way counter migration of the reacting cations from both sides across the spinel reacted layer. And whenever you have a faster ioning species than the other one, then you have preferential pore generation in the faster moving species side. So but in zinc aluminate, you see there is the zinc oxide has such a high diffusion rate that it's practically a one-way diffusion. So the zinc oxide is only diffusing on one-way side, and that gives a lot of pore generation in the zinc oxide zinc aluminate. So you see here, this is a BSE image. So the bright region is zinc oxide, the black one is alumina, and this gray one is zinc aluminate. And you see large amount of porosity at the zinc oxide zinc aluminate interface. So again, this is telling that this extreme Kirkendall effect of one-way migration of zinc ions is there, and that is causing. And this has been used in this Nature Materials paper, where they used a zinc oxide nanorod. They coated it with aluminum oxide and then heated at 700 degrees C to form zinc aluminate. And what happened is that the entire zinc oxide region was filled with pore, and they end up having spinel nanotubes, which is good for spinel nanotubes and sensors, but which is extremely bad for refractories because we don't want porosity in refractories. So the main goal is that if you can preform zinc aluminate and magnesium titanate as dense aggregates, which is cost effective, then that can be directly used in refractory, and that solves the entire problem. The thing about corrosion resistance and bonding, those potential is already there. We can solve this porosity issue, then we have a very high chance to make chrome-free refractories. Second, if we can quantify thermal expansion coefficient, so you can see this is from this is magnesia, and this is the matrix spinel. So this is magnesia spinel refractory. You can see that at the junction of this magnesia and this matrix, there is fracture porosity, and in this fracture porosity, the thermal shock induced cracks, they just get attenuated in these gaps. And so what means is that, why is this so? This fused magnesia grains has a very high expansion coefficient as opposed to this spinel rich matrix, and due to this thermal expansion coefficient mismatch, you get this fracture porosity, which is a good thing for better thermal shock resistance. So if you can quantify the exact thermal shock resistance, thermal expansion coefficient of these aggregates, then you have a better control in design of formulations for thermal shock resistant refractories. And that's why quantification of thermal expansion coefficient at 1600 degrees C is very important, which is normally not reported in literature. Secondly, we want to know how much the zinc aluminate phase bonds with commercial refractory phases like tabular alumina, like DBM, which stands for dead burn magnesia, and spinel. So there are four main parts: optimization of dilatometer, synthesis of magnesium titanate, zinc aluminate, and then bonding of zinc aluminate. So this dilatometer optimization that has already been published in this publication, and I'm going to go over the main takeaway points. So before getting into it, what you see here is that if you just use a dilatometer to measure the thermal expansion behavior of your sample, you get a very misleading data. This data is not useful at all. You need to correct this with the spacer calibration curve, and only then you get proper value. So how we do that? So this is the furnace of the dilatometer, which can go up to 1700 degrees C. So you have this alumina tube. A zoomed in picture of this is this. This is the push rod, and it is linked to a LVDT, which measures the which measures the change in length. And then you have these alumina spacers. There are two alumina spacers, and then there are these end blocks. So you put your sample sandwiched between these alumina spacers, and then you slide in the furnace and you heat it up and you measure the thermal expansion behavior. So first you measure the spacers, only spacers, and then you measure spacers plus sample, and then the spacers plus sample, you correct this with respect to the spacer. Let's show how it's done. So this is the alumina spacer calibration curve, thermal expansion, like relative change in length, the strain value versus temperature. This is the raw data, and when you correct this, you get this. And when you take a linear fit of this, that gives you very accurate thermal expansion coefficient values. And when you tally it with literature, and if it matches the literature values, so now your dilatometer is operating correctly. Now you can use it for your reaction studies. So there are three main points. One is that you have to calibrate it at the same temperature, same heating rate, and same dwell time. That is for your spacer. So what happens, you see here that when you're calibrating it with the correct spacer, so then you get the actual value. When you change the heating rate, if you use a faster heating rate, your thermal expansion coefficient changes. It becomes less. When you have an extra dwell time, but same maximum temperature and same heating rate, but different spacer, so that also changes the values. So you have to use the same spacer. You have to be very particular in how you measure the measure your sample, and then you have to put it on a polymer stand, damp proof, vibration proof stand, so which prevents these vibration induced defects. And then you have to clean the tube inside to remove like powder which can react with your sample as well as the tube. Now, once you have done all that and you have optimized your dilatometer, so you can study your pressed pellet directly, and you can see there is a sintering shrinkage of alumina and then impure alumina. And from this, if you do a temperature dependent strain rate, so you get this peak, downward peak, which tells you like gives an estimate about the optimum sintering temperature. And from there, the lower peak temperature means it sinters better. And I will be using these concepts later on extensively in my projects. Another thing which does is that, so this is in situ magnesium aluminate spinel formation, magnesium and alumina reacting. So you see that there is expansion of 7.6%, and there is a peak at 1485, and after this there is sintering. When you do a thermal derivative like temperature dependent strain rate curve, so you see that a spinel formation starts at 1050 degrees C. It is the fastest rate at 1150, and then it ends somewhere around like 1450, around that temperature. So now if you want to make phase pure magnesium aluminate spinel, should you calcine at 1050? Should you calcine at 1150? Should you calcine at 1485? You can do all these temperatures and do XRD, but there is a better technique, which is called step scan dilatometry. What you do is that you use the same press pellet, and you add steps in it, like temperatures. So 1100 degrees C, 1 hour soaking, 1200 degrees C, 1 hour soaking, 1300 degrees C, 1 hour soaking, and so on. And from there, you see that at each soaking time, there is expansion. And when the expansion stops, that's when your phase formation has completed. So 1400 degrees C is the temperature at which lab grade spinel formations completes, and we confirmed this with XRD. We got phase pure spinel. So this spinel has just completed reactions. It's highly reactive. It will give you very good sintering, and that's ideal for refractory manufacturing. So in conclusion, this dilatometric chapter tells you that you need to generate the alumina spacer calibration curve at the same heating rate and maximum temperature, and then you need to correct your samples like thermal expansion by data by that, which leads to reliable TEC values. And then you can use this temperature dependent derivative strain rate curves to accurately determine reaction temperatures, and it can help you estimate sintering temperatures of new compositions, which will be magnesium titanate and zinc aluminate in our work. So here we are comparing two titania sources. One is rutile, the other is anatase. Though they are in the same crystal system, but they have different unit cell dimensions. That's why they have very different XRD patterns. So the big difference between rutile and anatase is that rutile is denser than anatase. So during this reaction, MgO plus TiO2 equals Mg2TiO4, the rutile phase, since it is denser, it leads to higher volume expansion due to the density difference between them. So rutile gives you a theoretical volume expansion of 8.9% versus anatase, which is 4.5%, which is reflected in these two dilatometric curves. You can see here that when you use anatase, you are having a 2.4% linear expansion. When you have rutile, the linear expansion increases to 3.3%. Not only that, the derivative curves tells you that anatase forms, this anatase based Mg2TiO4 forms at 855 degrees Celsius, which is lower than that for rutile at 935 degrees C. So anatase reacts earlier. The third point, what you see is that there is this sintering, there is shrinkage, and this sintering, the optimum peak temperature is at 1175, which is much lower than the average of these two temperatures, which is, I believe, 1312. So again, this is almost 150 degrees Celsius lower than this. So from this lab grade raw materials, you get the proof of concept that anatase versus rutile, whenever you use them for as a TiO2 source for making magnesium titanate, it reacts earlier, anatase expands less, and anatase sinters faster. When you use industrial anatase and you react with industrial dead burned magnesia, which is DBM, you see that the expansion is much less, 1% versus 7.2%. This huge change. And what it does is that though after this expansion there is sintering, at 1600 degrees C, the shrinkage value is roughly 2%, whereas for rutile, the shrinkage value is 1% expansion. So this excessive expansion during rutile, when rutile reacts and forms magnesium titanate, there's excessive expansion hinders sintering. And that's what you see here is that when you have this 1300 degrees C, which was the optimum for the lab grade material, the porosity, the open porosity of the rutile based material was higher than the anatase based material. When you check the industrial grade material, the 1600 degrees C was the optimum temperature. There I found 0% porosity versus 3.8% porosity for the rutile based material. So rutile creates excessive pores and we do not want that. So this conclusively proves that anatase gives you a better dense aggregate, refractory aggregate, which is condylite or magnesium titanate refractory aggregate. When we did XRD, we found even further differences. We found that in terms of rutile, both lab grade rutile and industrial grade rutile, you have this extra magnesium titanate or gay-chelate phase. This magnesium metatitanate or gay-chelate phase has a lower melting temperature versus the desired phase, which is the condylite phase, magnesium orthotitanate, which is 1767 versus 1636. Not only that, this has poor corrosion resistance. So this is a very undesirable phase. There is an additional phase, calcium titanate, and this was present in all of the samples, even though it was identified only for the industrial grade materials because the calcium content was 0.75%, like 3 times that of lab grade materials. But calcium titanate is a good thing. It melts at a very high temperature. It's a refractory phase. It's fine to have it in the microstructure. So what you see here is that this in lab grade anatase, the calcium titanate is present in the intergranular regions. And we identified that with 0.8 ES, we found that almost like 1.1:1 calcium to titanium atomic ratio. And what you see here again is that in the lab grade material, you have some excess porosity. As we talked about, rutile creates more porosity. So next, what you see here is that industrial anatase versus industrial rutile. So you see the major phase is the gray phase, which is magnesium orthotitanate or condylite. We want that. There is some unreacted DBM, unreacted magnesia, which is the dark phase here, identified by 0.8 ES. And then there is this white phase intergranular region, which is calcium titanate, which is a good thing. It is good to have it. Just the titania phase actually reacts with the calcium impurity and creates a high temperature phase. But in terms of rutile, you not only have this excess gay-chelate phase, which is low melting, as well as it has poor corrosion resistance, but also you find that there is phosphorid magnesium silicate phase directly in contact with calcium titanate. And this is really bad because this magnesium silicate and calcium titanate, when in contact, it melts at 1490 degrees C, which is extremely low temperature. So this rutile is not useful as a refractory material, rutile-based magnesium titanate, but anatase-based material is perfect. The thermal expansion coefficient values tells that the lab grade materials always expand less than the industrial grade. This is because there is some unreacted magnesia present in the industrial grade materials and there is more calcium titanate present, and both of these have higher expansion coefficient than condylite phase, and that is why the expansion coefficient of industrial aggregates are higher. Also, you see a general trend that the thermal expansion coefficient increases with temperature, which we have confirmed later. The same relation holds for other refractory aggregates as well. That is why we need to quantify high temperature thermal expansion coefficient values so that we can design better thermal shock resistant refractories, because refractories, the ones which we are talking about, are to be used in steel making temperatures. So to conclude, what we see here is that the TiO2 particle size and the anatase to rutile phase transformation that assists magnesium titanate formation. We also see that when you have anatase reacting with DBM instead of rutile, the expansion percentage is less, 1% versus 7.2%. It reacts at a lower temperature, and then it gives you better sintering. And you have 0% porosity versus 3.8% porosity. Rutile forms low melting gay chelate phase, and also it has inferior slack resistance. And then it forms this intergranular low melting microstructure of phosphorite adjacent to calcium titanate, which melts at 1490 degrees C. Anatase based aggregate is the best. It has 0% porosity, 3.24 density, and 13.5 expansion coefficient. It is composed of magnesium titanate, the orthotitanate candylate phase, plus some unreacted magnesia and some refractory phase calcium titanate. And this magnesium titanate, this magnesium orthotitanate or candylite, can be used as a refractory aggregate, can be used as a matrix, as well as high emissivity coatings. Now coming to the zinc aluminate, we just got published this Sunday. So zinc aluminate aggregates, we are going to make dense aggregates, but before that, we want to start with something which is a known system, which is our reference system, industrial magnesium aluminate, made from DBM and calcined alumina. Both of these are very well-known raw materials used to make refractories. What you see here is that the spinel formation starts at 1150. It is the fastest at 1400 degrees C, and then it ends at 1500. After that, the sintering starts. So should we calcine at 1400? Should we calcine at 1550 or 1150? Step scan dilatometer tells you that. So at every soaking temperature, there is expansion, and this expansion stops at 1500 degrees C, which means that spinel formation expansion has ended. We calcined a powder at this temperature and we did XRD, and we found that there was some minor amount of unreacted alumina and magnesia in the spinel. And when we created pellets out of it, we pressed pellets and fired it at 1600 degrees C for 5 hours. All of this unreacted material was gone, and we are left with a dense spinel with 0% apparent porosity. When we compared the XRD pattern with commercial alumina-rich spinel, which is AR78 from Almatis, we found that the spinel peaks were shifted for the alumina-rich spinel to higher angles, which is because the alumina-rich spinel has a smaller lattice constant. So that means due to Bragg's law, the peaks shift to higher angles. So that's because aluminum ionic radius is smaller than magnesium ionic radius. So now coming to the zinc aluminate formation, what you see here is that as opposed to magnesium aluminate, you see that after the phase formation, there was some sintering going on. But in zinc aluminate, there is no sintering. For this lab grade alumina and lab grade zinc oxide, and this industrial zinc oxide and calcined alumina, which are the like the two representative industrial and lab grade materials. So there you see that there is no sintering after the phase formation. So when I used the same industrial zinc oxide but replace this calcined alumina by reactive alumina, I found that the sintering starts. The sintering actually happens quite appreciably. And this tells us that this zinc aluminate formation temperature is controlled by the alumina particle size as well as its sintering. You can see that the alumina particle size for this one was 0.9 macron, which is higher than this. And so the spinel formation temperature for zinc aluminate formation temperature was 1150, which is higher than 1000 degrees Celsius, just because of this particle size difference. And when you increase the particle size even further to 8.9 micron, the formation temperature increases to 1200 degrees C. So this formation temperature of zinc aluminate is directly linked to the alumina particle size. And using step scan dilatometry, we found that 1200 degrees C, 5 minutes is optimum for zinc aluminate formation from lab grade materials, whereas for calcined alumina, it is 1250 degrees C in 17 minutes. For reactive alumina, this was even less. It was 1050 degrees C for 1 hour. And these are the respective calcination temperatures which we used for preparing zinc aluminate powder, preformed zinc aluminate powder. And this step scan dilatometry was confirmed by XRD. We found single phase zinc aluminate in all of these respective calcined powders. And when we sintered, we found there is single phase zinc aluminate again, and there was very minor shift in the peak positions for zinc aluminate, which tells there is no significant sublimation after sintering at 1700 degrees C. So now we compare this calcined zinc aluminate powder sinterability with commercial and lab grade materials. So on the left hand side, you see only magnesia and spinel. You see that the DBM, which is industrial magnesia, has much better sintering. Much less sintering, it hardly sinters, whereas the lab grade magnesia sinters is 30% shrinkage versus almost like 1% shrinkage. So 1% expansion. On top of that, you see that the spinel shrinks faster, it has better sintering, and the stoichiometric spinel has better sintering than alumina-rich spinel, which is linked to their defect chemistry. So when you have alumina-rich spinel, it forms this cation vacancies, aluminum vacancies, and aluminum vacancies actually trap these mobile oxygen vacancies and form these defect clusters. So this actually reduces the concentration of mobile oxygen vacancies in the spinel. And since in spinel, out of magnesium, aluminum, and oxygen ions is the slowest moving species, so oxygen vacancy concentration is directly proportional to sintering rate. And since oxygen vacancy, mobile oxygen vacancies are reduced in alumina-rich spinel, so that is why the sintering is retarded. You see the three different kinds of aluminas here. Only the particle size is changing, and you can see that it is directly controlling the sinterability. The reactive alumina has the best sintering characteristics. And you see these red, blue, and black curves are directly corresponding to the zinc aluminate, which were made from these respective aluminas. And you can see that the sinterability of zinc aluminate is linked directly to the alumina particle size. So if you use finer reactive alumina, you will have more reactive zinc aluminate. So these are the main takeaway from these slides. And these are microstructures of the different magnesia we used. We quantified the thermal expansion coefficient, and why it was important, because you can see that the grain size of this is larger than this, and then this is a single crystal fused magnesia. So you will see later that the expansion coefficient is also scaling with the grain size. And then there you have alumina and you have the spinel. Now we also studied macrome because we want to replace macrome with zinc aluminate. So what you see here is that there is this white phase. There are only two phases present. One is the major phase, which is the gray phase magnesia in solid solution with iron oxide. You see the magnesium and iron overlapping. So there is this major phase iron oxide, magnesium oxide solid solution, which is in the periclase phase. And then you have this spinel solid solution, which is a solid solution of macrome and iron. So MgCr, LFE, that solid solution, you will have this intergranular regions. There is this bright phase which is highly concentrated chrome and aluminum in these regions. So there are two phases, the magnesia phase and the complex chromite spinel phase, which is richer in chrome and aluminum in the grain boundary areas as well as in intergranular bright regions. So I was telling you earlier, as the grain size of the magnesia increases, you can see the thermal expansion coefficient is increasing from 15 to 16 to 17. So we see a direct correlation between the grain size with the thermal expansion coefficient, and that can help in choosing between fused magnesia versus sintered magnesia in getting better thermal shock resistant refractories. In zinc aluminate microstructure, we see that in lab grade versus calcined alumina versus reactive alumina derived zinc aluminate, we found that in all of these samples, there was slight zinc oxide segregation at the grain boundaries, and the the calcined alumina, as it was calcined at a higher temperature, we found that there was more zinc oxide volatilization in this sample with respect to the other two samples, and that caused elongated grains. And we know, at least for spinel, that when you have alumina rich spinel, it tends to form elongated grains. But the takeaway message of this is that the in reactive alumina and industrial zinc oxide, when they react to form zinc aluminate, it gives you the zinc aluminate which is nearest to stoichiometric Zn is to Al ratio of 2:1. But we found that there were small minor unreacted zinc oxide present, which can be bond milled to remove them, and industries normally do that. So that can be easily resolved whenever this is industrially manufactured. So when you compare all of that, the thermal expansion coefficient, as I was saying earlier, that if you have a higher expanding aggregate in a lower expanding matrix, then you can have fracture porosity, which is a good thing for better thermal shock resistance. So when you have quantified all of these aggregates, then you can play around with this and design your formulation better. And in this picture, what you see here is that fused magnesia is the highest expansion coefficient, followed by dead bond magnesia, and then this fused macrome grains, and then you have zinc aluminate, which is almost same as tabular alumina and spinel phase. So this is very important in designing thermal shock resistant refractories. Moreover, you see that in all of these aggregates, there is a general trend of higher expansion coefficient at higher temperatures, which just means that you need to quantify your thermal expansion coefficient at high temperatures in order to predict the thermal shock resistance of your refractories. So in short, what we found here is that both industrial zinc aluminate and magnesium aluminate, they need a two-stage firing. The industrial zinc oxide and reactive alumina, they give the best aggregate with 0% porosity. They were fired first at 1050 to preform the zinc aluminate phase, and then pressed and fired at 1700 degrees C for full density. And then you see that the grain size of industrial zinc aluminate and magnesium aluminate were similar, and the pore size of zinc aluminate was very small, 0.5 microns, which can give better slag infiltration resistance. And then the zinc aluminate, this reactive zinc aluminate, which has been calcined at 1050 degrees C, it is an efficient refractory matrix material, as it possesses good sinterability, 8% shrinkage, which is more than magnesium aluminate spinel and calcined alumina. And then we have quantified the thermal expansion coefficients, and which can tell that potentially zinc aluminate can replace fused macrome aggregates to develop environment-friendly refractories. So then the final part of the PhD thesis is the bonding of zinc aluminate matrix. What you see here is that you have this aggregate which has been surrounded by the matrix phase, and we have sintered and polished from top to expose this, and that's what you are seeing here, the top view. You have the tabular alumina aggregate, and you have the zinc aluminate matrix, and I did point EDS, and what I found here is that there is something going on in the interfacial region. This is actually zinc oxide rich zinc aluminate, and the zinc, this is zinc rich, and the zinc oxide content is highest at this region where the zinc aluminate matrix just starts. So what this means is that zinc oxide actually has a high reactivity with alumina. So this zinc ion present in zinc aluminate is migrating towards this reactive tabular alumina grain, and it's forming this this zinc rich zinc aluminate phase, but it cannot penetrate fast enough because this tabular alumina is dense aggregate, it's a commercial aggregate. But all of this leads to direct bonding. You see there is direct bonding between this tabular alumina grain and zinc aluminate phase, which has been confirmed by 1:1 volume percent mixture of powders of these two, and we found that there is this shift of this garnite phase, the zinc aluminate phase, and we found that the alumina content also that was slightly changing. But we found that the alumina content was slightly increasing, which could mean that there was slight zinc oxide volatility from this zinc aluminate phase. We will compare it with macrome later on. But the main takeaway message is that there is direct bond formation between tabular alumina aggregate and zinc aluminate matrix due to this solid solution formation as well as this interfacial phase change. In zinc aluminate versus spinel aggregate matrix composition, we see that the direct bonding is so good that you can't even differentiate when spinel is ending and when the matrix is starting, which is very, very good. And when I magnified that, I found that there are these phase segregated regions. Both of these are like spinel zinc aluminate solid solution region, but there are certain spots which are magnesium rich and there are certain spots which are zinc oxide rich, and that's why you get this phase contrast. And when I did this point TDS across this, we saw that not only there is this magnesium ion diffusion towards the zinc aluminate side, there is as well as zinc oxide diffusion towards the spinel side, and the zinc oxide diffusion is deeper than the magnesium diffusion into the zinc aluminate side. So they form a very good bonding, and this is direct bonding confirmed with further with this high resolution image. You cannot tell where the two phases are ending, so there is like very good solid solution formation. So the direct bonding in this is happening due to solid solution. And by XRD, the only way which you can differentiate between zinc aluminate and magnesium aluminate is this peak at 49 degree. This is present in garnite, but absent in in magnesium aluminate. And we see here is that this garnite intensity is reducing. That means that a part of this zinc aluminate is going into solid solution with magnesium aluminate. Again, before and after firing, you don't see any zinc aluminate peak intensity change, which means that there is no sublimation of zinc oxide in this. For magnesium oxide DBM aggregate bonded to zinc aluminate, you can see that there is the zinc rich region. You see the bright contrast because zinc has a higher Z number. You can see that there is some migration, Mg diffusion into zinc aluminate, and obviously far more zinc diffusion inside the DBM grain. But from a microstructural standpoint, you see there is no direct bonding, and in fact, there is interfacial debonding. There is this gap. So they do not bond as good as tabular alumina and spinel. So XRD tells you that there is minor peak changes. Again, there was not enough solid solution formation, but then you see that there is very little. The black is the after firing, very little garnite intensity reduction, which is telling you that there is very minor sublimation of zinc aluminate. Now you see alumina, tabular alumina in contact with spinel matrix, and what you see here is that there is a lot of solid solution formation, and we all know this is alumina, this is spinel, there is this wide solid solution region. That's what you are seeing here. At high temperature in the interfacial region, there is this solid solution formation, and during the cooling of the sample, it precipitates this corundum phase. All of these bright ones, 7, 8 are corundum phase. So you have this high amount of aluminum in it with some solid solution of calcium in it and some magnesium. So this corundum is precipitating from this highly alumina-rich spinel present around these grains. So this confirms that in this alumina-rich spinel, as we are cooling, we are getting some corundum precipitation as well as some alumina-rich spinel formation. So all of this is leading to direct bonding between tabular alumina and spinel, and which probably tells why these materials are actually commercially used and they are known to have good performance due to this increased aggregate matrix bonding. The XRD tells you that there is solid solution, there is peak shift. Alumina-rich spinel, I told earlier, it shifts to higher angle because aluminum has a smaller ionic radius. It reduces the unit cell size. That's why the peak shifts to higher angles. And as well as you see that the alumina percentage is reducing, the alumina intensity is reducing because the alumina is getting consumed in solid solution formation. In bonding of DBM, which is magnesium aggregate with magnesium aluminate matrix, you see there is interfacial debonding, there is no direct bonding, and there is very little solid solution of aluminum into the DBM, and we don't see much changes in the spinel peak shift. So, but we see there is some changes in the spinel intensity. The spinel intensity is increasing. That is why, this is because this lab grade spinel was calcined at 1400 degrees C, and when we did XRD, the spinel grains were just formed, the spinel crystals were just formed, so they did not have enough, enough properly formed crystals were not there. But when you sintered this entire thing at 1600 degrees C for 5 hours, this higher temperature, 200 degrees Celsius higher temperature, and then longer firing time, gave the time for the spinel crystals to form properly, and that is why you see this increase in the intensity of the spinel peak. Now this macrome, macrome, direct bonded macrome is highly used in the refractory industry, and you see that this in the magnesium matrix, this macrome grain is there, and if it was fired at the same temperature, you see most of the chrome is gone. You have just a little bit of chrome left, almost half of it is gone. That means that there is a lot of volatilization of macrome at this temperature. So what you see is there, we all know there is direct bonding, and you can see that there is chrome across the interface. There is chrome on both sides, chrome and aluminum, and the peak shift is also telling you that there is this magnesia is taking in chrome into it, so that is why there is a peak shift. But you see here is that the spinel phase, the intensity of it after firing is almost gone, which means that there is a lot of sublimation of macrome as opposed to zinc aluminate, where we found there was minor sublimation. And this is a very big thing, because a lot of people were like, one of our reviewer comments in our recently published paper was that you talk about the sublimation rate. Does zinc aluminate has a higher sublimation, or does it has a lower sublimation? And now we know that zinc aluminate is much better than macrome in terms of sublimation. So if I summarize this, we found that direct bonding was present in zinc aluminate, where zinc aluminate matrix in combination with spinel and tabular alumina aggregate, and this same direct bonding was present in alumina, tabular alumina with spinel matrix, and then fused macrome with magnesia matrix. There was interfacial debonding, meaning there was no direct bonding present in both DBM aggregate when it was present in zinc aluminate matrix or spinel matrix. So whenever you have DBM aggregate, it does not have direct bonding, except only with macrome, when you know that chrome and magnesia, they form a direct bonding. So we found that there's relative diffusion of zinc from zinc aluminate in DBM was highest, then followed by spinel, and then there was none in alumina. But in general, better direct bonding results when there is more solid solution, which was found in spinel and zinc aluminate, and when interfacial phase changes occurred, as was found in zinc-rich zinc aluminate region in alumina zinc aluminate, and corundum precipitated alumina spinel region in alumina spinel region. So solid solution with tabular alumina, we found that spinel goes into higher solid solution than zinc aluminate, and quantitative XRD showed that sublimation of macrome is much higher than zinc aluminate. So overall, if I conclude, what are the key takeaway points from this PhD dissertation? They are, you need to optimize the dilatometer by calibrating your spacer, and then use that spacer calibration curve to correct your sample. Then we found that anatase gives versus rutile, anatase gives lesser expansion, it gives earlier reaction, and then better sintering. It gives you 0% porosity. So we have made refractory aggregates which can be used in the industry. Then zinc aluminate, we have prepared that zinc aluminate from industrial zinc oxide and reactive alumina is the best. It gives you 0% porosity, 4.44 density, and then 0.5 micron pore size. So these can be used as an aggregate, and also the calcined powder at 1050 degrees C sinters better than industrial spinel and calcined alumina, so it can be used in the matrix in castable and brick formulations. When we compare the thermal expansion coefficient, we found that zinc aluminate expansion coefficient is similar to tabular alumina and spinel, but lower than magnesium titanate, macrome, DBM, and fused magnesia. So these values at 1600 degrees C and between 1600 and room temperature, this will help you in designing thermal shock resistant refractories. And when we compare the bonding, we found that direct bonding is present in spinel zinc aluminate interfaces, tabular alumina zinc aluminate, and alumina spinel interfaces, and chrome and magnesium interfaces, but it was absent for DBM with both zinc aluminate as well as spinel. And lastly, we saw that the volatilization of macrome was higher than zinc aluminate at 1600 degrees C in air. In future work, it can be done that we need to study the bonding of magnesium titanate matrix with the commercial refractory aggregates, so that this will tell whether magnesium aluminate should be added as an additive to magnesia, spinel, or alumina. And also we can check the sinterability of the magnesium titanate powder, which can help in comparing its sinterability with the other matrix materials used in the refractory industry. Finally, we can make some custom made. We just got our slag cup pressing mold, so we can press a cup made of our different 5 compositions, and then we can put some synthetic slag in it, and we can fire it at 1600 degrees C 3 hour and do SEM ADS and XRD, and maybe support those with fact-based thermodynamic calculations to compare the corrosion resistance of zinc aluminate versus magnesium titanate versus spinel. So that concludes my work, and I'm thankful for funding from DOE project as well as ASTM International and all my funding for, and also the industrial raw materials from Harbison Walker, Almatis, US Zinc, and Chronox were extremely helpful. And I thank all the technical discussions I have and my co-authors as well as the committee members. Thank you.